In this video segment, we're going to be talking about thermodynamics, the basics of heat transfer. What is heat? Heat is a form of energy, and we can use that energy for our benefit in packaging. It helps keep cold things cold, warm things warm, or blocks heat and blocks cold when we need it to. So we're going to use these basic concepts of thermodynamics and apply them to passive packaging for cold boxes, for instance, or vaccine carriers, other insulated packaging materials. All drugs are sensitive to temperature. It's just that some drugs are more sensitive than others. Vaccines, for example, some can't be frozen, yet all vaccines are sensitive to excessive heat. What that does is it affects the quality of the drug. We want the drug to be of high quality and as efficacious as possible by the time it gets to the patient. So when a drug is being transported, the hazards of the transportation environment are great. Exposure to heat and freezing can occur while the drug is being transported. So we protect them using insulated packaging materials and temperature stabilizers to maintain the quality of the drug product and maintain a specific temperature within that package. What is heat? Heat is energy transferred on a molecular level from an area of higher temperature to an area of lower temperature. Heat always moves to cold. The process by which heat energy is transferred through direct contact is called conduction, like we see here. The handle of the pot is hot. We can't grab it with our bare hand or we'll get burned. So what do? We put insulation in between our hand and the hot handle of the pot. Now some materials, such as metals, are great conductors of heat, while others, such as wood, are not. This is why when we grab both of these materials, the metal spoon feels colder than the wooden spoon, when actually they're at the same temperature. But because they transfer heat at a different rate, this feels colder because it's drawing the heat out of our hand than the spoon. Now this is really important when we apply this to packaging concepts, because the lower the heat transfer, such as the spoon, the better off we're going to be, the more insulation value it's going to provide. Now a second form of heat transfer is convection. We can see the transmission of heat through transporting a group of molecules through a fluid substance such as the boiling water. As it heats, the molecules are released into the atmosphere. And finally, radiation, or the transfer of heat energy without the involvement of a physical substance. The flame underneath the pot is providing the heat transfer. Radiation can occur in a vacuum. The light we get from the sun as it warms us when we lay on a beach. That's a classic example of radiant heat. So these are the three types of heat transfer that apply to insulated packaging. Let's take a closer look at them. Now we can take these three concepts of heat transfer and apply them to package design. For instance, our insulated packaging system, the insulation acts as a thermal resistor, blocking the transfer of heat. The more that we can block that heat, the better off we're going to be in the long run, because our product is going to be better insulated and better protected. Now the refrigerants that we use inside the package to help keep the product cool actually acts as a thermal capacitor. It stores and releases heat energy. So how we can apply this thermal resistance and capacity information with the refrigerants in packaging we'll take a look at in another video. Now there are other considerations to take into account other than conduction, convection, and radiation when we're designing our package. For instance, we need to know what the material is that we're working with. What is the size of the material, the total surface area, the mass, the volume of the product, and the ambient temperature to which the product is going to be subjected when it's in transport. All these are very important concepts when designing our package and being able to protect our product. You need to know what type of insulation material you're working with. There are different characteristics among materials, and some insulate better than others. Expanded polystyrene, for example, is a pretty good insulator, but polyurethane insulation is better. And finally, vacuum insulation panels provide the most resistance to heat transfer. So in this application, it's sort of a good, better, best approach to insulation. Now the surface area of a box is also important. We talked about earlier about the specific heat of a material. Well, sometimes the larger the surface area of the box, the more heat that it can absorb. This is why we want to choose an insulation material that has a very low heat transfer rate. Also, the mass of the product. Is it a dense product? Is it not so dense? What's its ability to absorb and store heat? And finally, the volume. Larger volumes of liquid, for instance. Liquid is a great heat capacitor, so it has the ability to maintain its temperature for a long time. If we're dealing with small volumes, 1 ml or a half an ml, the heat exchange is going to occur much more quickly than, let's say, if we have a vial that has a 20 ml fill volume. So the elements of thermodynamics that we've talked about to this point are pretty much things that we have good control over. We can control what types of materials we use, how much refrigerant we put into a package, what size our package should be, how much volume we put into that package. But what we didn't talk about is perhaps the most influential and important element of the thermodynamics process for a package, and that's the environment in which it will travel. The external temperatures have a profound impact on the performance of a package. In an insulated packaging system, the insulation acts as a thermal resistor, slowing the transfer of heat in and out of the walls of the package. The refrigerants act as a thermal capacitor, sort of like a battery. It's able to store energy, and then as heat is resorbed, it releases that energy. For instance, if we design our package to meet a certain amount of total heat during distribution, and that heat is exceeded, as that heat is entered into the package, it's absorbed by the refrigerants. If it's too long in that environment, an equilibrium will occur inside that package, and eventually the inside of the package is going to attain the same temperature as the outside of the package, because all of the energy that we had stored up in our capacitors, our refrigerants, has been used up. Now conversely, if we take a box that has a specific amount of energy in it, and we're trying to maintain a specific temperature, let's say 2 to 8 degrees C, and we put that into a colder environment, let's say a refrigerator that's at 2 degrees C, or into a freezer, what happens? Well, we know from the basic concepts of heat transfer that heat moves to cold. So if it's now warmer inside the box than it is in the surrounding environment, then the heat is going to be taken out of our product and out of the package into the atmosphere. What happens? Our product freezes. We take it out of that environment, send it along its merry way in the transportation environment, and what happens? The heat on the outside of the package is now greater than the inside of the package. So our product is no longer frozen, but it thaws. It turns to liquid. And by the time we receive that package, we open it up and everything looks fine. We have our liquid in our vial. Now, these principles of thermodynamics and the concepts of heat transfer that we talked about have all been applied to the design and qualification of cold boxes, vaccine carriers, and other insulated packaging systems. It's critically important to use vaccine carriers, cold boxes, and other insulated packaging systems as they were designed, and not to deviate from them.